Okay, so we're back, and now we're going to do the next level of complication, which is we actually have something that melts. So we have a 4 kilogram minus 10 degrees C. Okay, that's its temperature. Block of ice. I'm using ice in inverted commas because I'm not going to use the correct value for the specific heats because I want to keep the math simple. So I'm cheating. So it's not ice really, but it's ice because it's got the same melting point and you can visualize it as ice. It's dropped into a calorimeter that contains, and this is going to be 8 kilograms, 20 degrees C water. Now, show that the equilibrium temperature is that. That's the answer we're looking for. Specific heat for ice is equal to 2 joules per kilogram degrees C. And the specific heat for water is equal to 5 joules per kilogram degrees C. And then we have the latent heat of crystallization is 6 joules per kilogram. And I actually have the latent heat of vaporization, but nothing vaporized in this. We agreed on that? The solid becomes liquid, and that's the end. So that's just, a bit of a red herring there. I say that my change in Q is equal to 0. So now, I'm going to, if only for a minute, I'm going to think back about this diagram. I start off with ice below its melting point, so I need one term for the warming of the ice. I need another term for the melting of the ice. And then the ice water gets heated up to its last final temperature. And all of this is paid for by the cooling of that hot water. Does that make sense? Conceptually? I'm doing 3 things to the ice. I'm heating it up to its melting point. I'm melting it, and then I'm heating it up to its final temperature. Doing 3 things to the ice. I'm doing 1 thing to the water. I'm cooling the water down. That's 4 things. I need 4 terms. Most common mistake in this, people just miss a term out. They forget about raising the temperature of the melted ice water to its final temperature. They just forget about it. So you've got to be careful about that. So then I say, well, I have the mass of the ice times the specific heat of the ice times the temperature change for the ice. Let's do it vertically because it just seems to lend itself a bit better like that. Plus the mass of the ice times the latent heat for the ice. Now I've melted it. Then I have the mass of the ice. It's still ice, but now it's water. Agreed? It's the same molecules that were ice, but now they're water. Agreed? They're melted. So it's still the same mass, so I'll call it mass of the ice. If you like mass of ice water, if it makes you feel better, but it's the same as the mass of the ice. Times specific heat of water. It's no longer ice, it is water. Times the temperature change for the ice water. Plus the mass of the hot water times specific heat of water times the temperature change for the hot water. Is that conceptually what I'm doing? And all of that equals 0. Does that make sense? Yeah? 4 bits. So then I go mass of ice, specific heat of ice. Now, temperature change. What's the final temperature of the ice? Is it T final? Is it that? No. It is what? What does ice melt at? 0. 0 minus. What is the initial temperature for the ice? Ti. Plus the mass of the ice times the latent of crystallization plus the mass of the ice, water, specific heat of water. What is the final temperature for the ice water. I don't know it. I've given it here, but I don't know it. It's T final minus. What is the initial temperature? What is the starting temperature for this ice water? 0, because it melted from ice. Plus the mass of the hot water, specific heat of water. Final temperature of the hot water is T final, yeah? What was the initial temperature? T hot water. And that equals 0. I'm going to get rid of, oh man, I keep doing that, don't I? I'm going to get rid of that because I don't need it anymore. I got my 4 terms. So then I go mass of the ice. Looking at my diagram, 4, 2, 0 minus 10 plus 4, 6 plus 4, because it's just the same molecules, 5, TF minus 0 plus 4, oh no, now this is the hot water, 8. It's water. It's water. So that's going to be 5 again. TF minus, it started off at 20. So I've run out of space on the side, so I'm going to go to the bottom. So I'm going to do that and see if I can help myself. So that's going to be 8 times 0, which is 0, minus 8 times 10 is 80. There's my first term. Plus 24 plus, this is going to be 20 TF minus 0 plus 40 TF minus 800. Grab your TFs and put them together. 60 TF is equal to 80, 104. 104, 800 minus 104 is 696. It's 800 minus 104 is 696. So TF is equal to 696 over 60, which equals 11.6 degrees C. Yeah. Yeah. Not bad. Not bad. 3 bits, yeah. This next bit, what language am I using here? So in the homework, it might say Gluck and sip. Just to, sip is liquid, Gluck is solid, But I decided that it's better if I give you something you can visualize. And, I don't want you getting all distracted by what is Gluck, So let's call it butter. And let's call the liquid oil, cooking oil, olive oil, not butter, not liquid butter. It's a different stuff. It's liquid, it's oily, but it's different. So we have 2 immiscible liquids eventually, yeah? What difference does that make? So I have a 3 kilogram, it's at 15 degrees C, block of butter, and it's dropped into a 10 kilogram, 40 degrees C vat of oil. And we know that the specific heat for the solid butter is equals 2 joules per kilogram degree C. Oh, specific heat for the liquid butter, that's interesting. That's 5 joules per kilogram degree C. And the latent heat for butter, latent heat crystallization, is 6 joules per kilogram degree C. And the specific heat for oil is equal to 7 joules per kilogram degree C. And the other thing I need is that melting point for butter is 20 degrees C. What am I doing? What steps am I taking with the butter? Step 1, I heat the butter up to its melting point. What's step 2? I heat the butter up to its melting point, then what do I do to the butter? I'm taking this butter, I'm putting it into hot oil. The first thing is, the butter heats up to its melting point. Then what does it do? It melts. So it's liquid butter. Then what does it do? It heats up to its final temperature. 3 steps. What do I do to the oil? I've not got a heater on the oil, it's just warm oil. What do I do to the oil? Cool down the oil. 4 terms. I say delta Q equals 0. I'm going to get the mass of the butter times specific heat for solid butter times the temperature change for the solid butter plus the mass of the butter times the latent heat for butter plus the mass of the butter times specific heat for liquid butter times the temperature change for liquid butter plus the mass of the oil times specific heat for oil times the temperature change for the oil equals 0. The mass of the butter, specific heat for solid butter times, I'm going to have trouble writing this down, melting point minus T butter. Yeah? You go from the temperature of the butter to whatever temperature it melts at, plus the mass of the butter times the latent heat, plus the mass of the butter times specific heat for the liquid butter, and the temperature is going to go T final minus melting point, plus the mass of the oil times the specific heat for the oil times T final minus T oil. Let's get some numbers. 3. Solid butter. 2. Melting point. 20 minus, how cold did it begin? 15. These are all positive temperatures because it's not ice, it's butter. That was a little bit weird, but it's okay. 3 times latent heat is 6. 3. Specific heat for liquid butter is 5. Temperature change, T final minus melting point. Melting point was 20. Plus, looking down at the bottom now, 10 times specific heat is 7 times T final minus, and how hot was this? Oh, 40 degrees. All of that equals 0. 4 terms. 6 times 2, that's 120, minus let's do it this way. Let's make it a bit simpler. 20 minus 15 is 5. 5 threes are 15. 2 15s are 30. 6 fives are 30. There's that. Plus 18. Plus 15TF minus 300. 15 times 20 is 300. Plus 70TF minus 280. I think that's right. Or is it 2,800? 2,800 equals 0. 15 and 70, 85 TF. Minus 2,800 becomes plus 2,800. 2,800, 2,500, 2,470, 2,452. I think I'm right on that. $2,452 divided by 85 equals, I'm getting 28.8. Ooh, I made a mistake.
You did 2,800 minus 300, so plus.
Oh, thanks ever so much, yes. So it was not. So rush in. 2,800 plus 300 equals minus 30 equals minus 18 equals 30.52. So that's 30.52 divided by 85 is equal to 35.9. Let's just highlight a few things. If we compare these last two examples, the difference is that whereas that specific heat is different from that specific heat. When we had ice and water, they were both the specific heat of water. I'm sorry. Did that again as well. Whereas that specific heat is different from that specific heat. In the previous example, they were both water. So they were the same numerical value. That's one difference. And then the other difference was that we knew before that the melting point of ice is 0, and now we don't know what the melting point is. So we've got to numerically pay attention to that. That's the only two numerical differences in the calculation. It's a very similar problem, but it looks very different. You know, mathematically, there's just that one little wrinkle. It's not ice becoming water. It's butter becoming liquid butter, not oil. And then you can't assume that the melting point is 0. Most common mistakes in this is they'll forget an entire term, or they'll put down for this one here. They'll put down final temperature. They won't put melting point down. They'll put final temperature down because they're not thinking in terms of 4 steps. They're not thinking through the steps. They're trying to just remember the math. If you look at each one of those things, it's kind of trivial. You know, it's just the mass of something times the specific heat times its temperature change, or it's the mass of something times its latent heat. It's kind of mathematically really straightforward. The problem is, what do you apply the math to? And that's the visualization. So I would encourage you, as always, I'd encourage you to ask yourself, what's going to happen to this body? 3 things are going to happen to the body. What's going to happen to oil? 1 thing. Now let's work out what those things are. And it'll look after itself. Next time, we're going to go into thermodynamics. So we'll talk about that. Let's just, I've got your test stand back, but before we do that,